Okay, hello everyone. It's good to be here. So today I'll be talking about games. It will be a story of search in games, and we will look at the history of computers beating humans, and most notably I will focus on a game of poker. So what is DeepStack? DeepStack is the first computer AI to beat professional humans in poker. So let's have a look how we managed to do it, and let's have a look at some nice theory. Okay, so games have always served as a frontier for AI. So why is that? We have always dreamed as humans to create machines that can outperform us in many tasks. It turns out games are an easy task to measure, whether the computer was able to beat us, and it's also not a deadly task to do the measurement. And as you can see up there, there you have a list of some remarkable milestones throughout the history, where these results were either, for the first time, computers were able to beat us as humans in some of these games, but also the results presented here bring something new, some new ideas, new algorithms, and we will have a look at what's the new thing that DeepStack brings. You can also see my simple drawing of something I call a game tree. And let's spend a few seconds together to talk about game tree, because that will be a crucial notion throughout my talk. So game tree is very, very simple. Think of it as these nodes, these small circles. These are the state of a game. In chess, it's a simply chess position, some formation of stones on the board. We can also see some edges, and that's, yet again, super simple. These are the actions that are available for a player in this particular state. Taking an action for a state that moves the game to a different state, and so on. So it's not hard to see that this is a simple tree. And to make most of my arguments even more simple, I will often simplify it as the blue triangle up there. So whenever you see triangles, think of these tree-like structures with some nodes, some actions, and so on. Okay, now let's have a look let's have a closer look at the games mentioned up there. And as I promised, this will be a story of search. So let's have a look what the search is and why it's important for games. So on this slide, as you can see, suddenly I separated the games into two categories. The first category, that's the category up until 2016, where we had the amazing result where we were able to beat humans in Go. All these games are games that we call games of perfect information. So what is a game of perfect information? One way to think about it is that given an observation to a player, there's only one state that is consistent with that observation. Now, this formulation may seem a bit cryptic, but all I'm saying is that if I see a position in chess or in Go, there is only one game state that corresponds to that observation. Nothing spectacular. In poker, it's not hard to see that's not really the case. Given my observation in poker, there can be many different states of the game that are consistent with that observation. Again, what I'm really saying is then that when I see my cards, I can see how much money my opponent already put on table. There are many cards that the opponent can actually be holding. So I have some imperfect information, some uncertainty about the state of game or about the state of world. And it's not hard to argue that our world, the world that our agents as humans live in, indeed is a world of imperfect information. We never get to observe all the information that's up there. So in this sense, poker is somewhat closer model to reality than the previous games are. Now, why is the line important there? We finally get to the story that I promised to tell you, the story of search. So for all the games that I put there, above the line, if you look at IBM Deep Blue, if you look at TD Gammon, if you look at Atari Games, if you look at AlphaGo, even though they internally used somewhat different ideas, whether they used Monte Carlo tree search, minimax algorithms, neural networks, whatever there was one crucial idea behind all these algorithms that made them work so well. And this crucial idea is the key thing in our story, and that's the idea of search in games. So think back for the first slide that I presented, the one with the triangle, the game tree. So what I was trying to explain is that we have some states, we can make some actions, and these actions lead us to different states. Now, what does it mean to search in this game tree? All it means is when I am in a state, I look at the board in chess, and I'm about to figure out my move that I do believe is going to win me the game. I am going to consider all the future moves. So I am basically saying to myself, well, okay, if I move this pawn over here, or if I move this bishop, what game state do I get into? And I'm also considering all the possible counter moves of the opponent. So I'm looking forward in this small game tree that we've seen previously. I'm looking few steps ahead. Now, if I'm lucky enough and I can look forward deep enough so that I can see lines that actually lead till the end of the game, so that I actually see that if I do this, opponent does this, and then I can do this, there's a checkmate. It's easy to see that this is a line I should follow. So that's one key ingredient, like looking forward. Unfortunately, it's unlikely that I will be able to consider all the moves that can happen forward till the end of the game. So what we usually do, also we as humans, we look only a few steps ahead, and then say we look at the future board and think, well, if this line happens, so if I make this move, opponent makes this move, I'm going to win a queen. So maybe winning the queen is a good situation for me. I don't have to think about this situation anymore, because I do believe this situation is good for me. So the thing I've done just now, I evaluated the state where I just won a queen. So this is another crucial ingredient in the story of search. Not only that I'm looking forward, few steps ahead, but also I'm using something to evaluate these future states. And again, that can be some fancy neural network, it can be some simple if-else rules, or it can be any other table. So it's a function from a state to my estimated value of that state. So these two crucial ideas are at the very heart of search. Having these two ingredients, all I do is follow steps 1, 2, 3, 4. I look few steps ahead, I evaluate the future states, I make the action that I do believe is best based on my search, and then I will just make this action and I'm done. What I've done is I've moved one piece on the board and I wait for a next situation to happen. I wait for an action from my opponent, and once I am to move again, I will again do 1, 2, 3, 4. So it's easy to see that following these steps works in the sense that I'm going to play chess. Now the question is, am I going to play chess well? It turns out we can say that we will play game well only for games with perfect information. So this very simple idea that sounded trivial, like there can be nothing wrong with this situation, right? I'm just looking forward, I'm evaluating future situations, and making best action based on my evaluations. So all of that works, except for games with imperfect information. That's the line. So the fact that it doesn't work is very unfortunate, and that's also the reason why poker took us so long to figure out how to make agents that can beat humans. So now let's have a closer look why this breaks. So think about 3 friends, all of them very good poker players. Let's say that all of them can play chess optimally. All of them know how to follow an optimal strategy. It's just each one of them knows a different strategy how to play chess optimally. So we have these 3 different colors corresponding to a strategy, and every single game node of our game, and every single one of our friends, if he were to follow one of these lines, it would be an optimal strategy. Now, what if our friends are lazy and they want to go to a bathroom in the middle of game? So what if the friend in the middle is the one who starts the game, and in the middle of game he just leaves the room and asks one of his friends, "Hey, can you please finish the game for me?" So the blue friend comes there and follows the situation. He looks at the board and does the search again. He will play his optimal strategy from this node onwards. So looking at these colored triangles, all I'm really saying is that if we combine these colors together, the resulting policy of these three friends playing looks like this. Basically, in all the game states in the game tree, in here, we will follow decisions of the green guy, and in here we will just follow the policy or strategy of the blue guy, and so on. So this is a resulting strategy, is a combination of these 3 friends. Now, it turns out that this simple combination of strategies, that is our friends going to a bathroom, going to movies, and just playing the game this way, this again works only for games with perfect informations. So what I'm saying is that the triangle down here, this strategy is optimal only if it's a game of chess, game of Go, game of backgammon, but it doesn't work if it's a game of poker. So this sounds that we are lost. Even if this simple reasoning doesn't work in poker, how can we reason locally about the game states if this simple combination of optimal policies doesn't work? So that's indeed why for the last, say, 20 years, computer poker research basically abandoned this idea of doing a local search. And we rather used a very different approach. This approach was called Abstraction Techniques. And if you were to look into literature, say, till 2015, 2016, and look at some surveys, this is what you have learned. The reasoning was very much the one we did just now together. Trying to solve this large triangle independently, so solving these small pieces and somehow gluing them together doesn't work. So let's rather make a smaller game out of the large one. Solve the full game in here. Hopefully this one is small enough so that we have only one friend that can play all the game. So we will solve this small game, and then we will somehow map an optimal policy from this game back to the large game. Now this might seem confusing with all these triangles and abstractions and solving. This is what it really means. If we were to use the same idea, the fancy idea of abstraction techniques from all the leading papers in computer poker, and we wanted to use the very same idea in chess, we would take the large game tree in chess, we would create it a smaller game so that it's small enough we can think about the full game at once, find an optimal policy in this small game, and hopefully try to play the same optimal policy somewhat back in the full game. Now on chess, this seems rather silly on my picture, right? So maybe it's also silly in poker, maybe it's not. Now, if you guess that it's silly in poker as well, you've guessed correctly. So one way to measure how good the agent plays poker is something that we call exploitability. And there's two ways how we can think about exploitability. One is worst case winnings against some unknown opponent. So say you think that you know how to play poker, exploitability measures what's the highest amount you can lose against an opponent that really knows how to beat you. Other way how to think of exploitability is how close to an optimal policy we are. So exploitability of 0 means the strategy is optimal. The higher the exploitability, the worse the strategy. So this is a table with all the leading computer agents in 2016. As I said, the higher the worse. And these numbers by themselves wouldn't really tell you anything. It's just some number, and what number is good, right? To give you some intuition how bad these numbers are, consider the last strategy down here. This is an agent that if you were to implement it, it's a 1 or 2 line piece of code that folds every single hand in poker. So I'm not sure how familiar with poker rules you are, but even if you are dealt, say, a pair of aces, you would just give up the game, give the money to your opponent, and that would be your policy. So this policy or strategy is provably closer to an optimal one than all the leading agents in 2016. So indeed, the naive picture we had in chess, something similar was probably happening in poker. Now, okay, maybe we are not close enough to an optimal policy, but we are still good enough to beat humans, right? So let's say we try to take these abstraction agents and run it versus professional poker players. So that's what in 2015 Carnegie Mellon University indeed tried, and with a limited success. No, not only they lost against humans, but it also showed another issue with running computers against humans in poker. The game of poker is inherently noisy. What I mean by that, we have to play a lot of games versus humans to be able to say, okay, I'm pretty sure that I am beating humans. The noise comes just from the fact that there's some randomness in dealing cards, right? So if we win 1 or 2 games, maybe we were just lucky and got good cards. So we have to get enough data to get us some statistical intervals to say, well, okay, we are in 95% confidence interval that we are beating humans. So not only the 2015 match showed that humans are pretty much beating the computer, it was also hard to say it within statistical significance. And that was all due to the noise in poker, even though people were forced to play 80,000 heads of poker, which is quite a burden. Okay, so clearly, not only the approach that we just described doesn't work when measured to when measured in terms of exploitability, but it also doesn't really work against humans. So let's come back to the idea we dismissed previously, the idea of local search. So DeepStack is all about fixing the idea of local search and bringing all the nice properties of local search back to imperfect information settings. So to go through all the details, we would be here way longer than the entire workshop is in here. So let me give you just a small taste of what DeepStack needs to do to fix the local search. So you can see the 4 points that we discussed previously when we described local search. These 1, 2, 3, 4, look forward, evaluate, make action, repeat. DeepStack follows similar steps, except there are 2 subtle but crucial differences. Number 1, the local search reasoning doesn't start just looking at the state, but also needs to keep track of some invariant that helps DeepStack to be provably close to an optimal policy and does not struggle with this combining locally optima together issue that we discuss with these colored triangles. So that's number 1. Number 2, we also have to reason about future states differently. In perfect information games, say for chess, it's easy to see what's a state. It's just the board, and this is what our neural network gets as an input to evaluate. In poker, it's a bit harder to argue what should be our state, and we will see on the next slide what the value function needs to be for DeepStack. But other than that, we do pretty much the same. Based on our reasoning process, we pick the action that looks the most promising, we make the action, we update this invariant that we needed in step number 1, and we repeat. Now, one way to think about this magical invariant in there is when we were thinking about local search as our friend going to a bathroom and the other friend just joining the table and playing the chess game onwards, there was no communication between friends. One way to think about this invariant is our friend who leaves to a bathroom to put some small note on the table for our friend, and the friend who sits behind the poker table, here it's the small note that helps him to play correctly so that he doesn't screw up what our friend who just left was hoping to do. Okay, now I promised you to also show you what's the difference in value function. So on the left, we have a value function for perfect information. So neural network, or any value function really, gets as an input some representation of the board. For AlphaZero, it really is just a picture that we feed through convolutional neural nets. For DeepStack, if you recall slide number 2, I told you that in imperfect information games, there are many states consistent with a single observation. So I see something, but there can be multiple states that would give me the same observation. While in chess, there's only one state that gives me this exact observation. So in imperfect information games, not only did I put this observation as an input to my value function, I also put some distribution over these possible states sharing the same observation. So this is the crucial difference in value function for perfect and imperfect information games. Now it's not hard to see that the value function on the right is strictly more general than the one on the left, simply because our distribution can be over one state. Now, does it work? When we finally fix the idea of local search and we don't have to do the silly abstraction thing, will it get better? So first thing to look again is the exploitability. That is, how close to an optimal policy we got. So this is the same table, except that up there you can see DeepStack. And the reason the number is negative is not that the exploitability is lower than 0. It's just because the game is so large, for all the agents except for always fault, we can only estimate the value. For always fault agent, we can compute it analytically. For the agents up there, we can just do our best to get some lower bound on the exploitability. And this graph just tells you that the best technique out there that tries to give you some bound on the exploitability is unable to get any exploitability whatsoever from DeepStack. Now, that just suggests that we are now much closer to an optimal policy. But is it enough to finally beat humans? And that's exactly what we did in 2017 or in 2018. In 2017, we were able to beat humans. And in 2018, we got the publication out there. So some crucial findings. The win rate itself, this number will be probably interesting just for people who play poker. But just trust me, the win rate is quite big. This really is not just beating humans, but indeed humiliating them. We also have a pretty high confidence interval for the win rate. So we also fixed the issue with we need a lot of data to be sure that we won. The implementation itself can run on a single GPU. Actually, we were able on some presentations to run DeepStack on a single gaming laptop. And the thinking time, the local search procedure that looks at the situation and thinks before it makes an action. So it takes only 3 seconds on average for DeepStack to make the action. You can also see why one of the players, probably the most famous one in our study. As you can see, we played people that do know how to play poker. So this slide I'm going to skip because of time. All I want you to bring home from this slide is there's a clever way how to get statistically significant result from noisy data with using much less data that you would need. All I want you to remember is this number. Our technique uses only 60,000 data points to get us the same statistically significance as if we force humans to play it over million games. Okay, perfect. So to conclude, so what is DeepStack? DeepStack is the first computer AI to beat professional humans in poker. Crucially, it's not just what we did, but also how we did it. It's the idea of bringing local search techniques to imperfect information games. We use deep neural networks as a value function that evaluates these states in imperfect information settings. We used no human data for training the neural networks. All the data was trained from some version of self-play, if you wanted to call it this way. And this study was published in May 2018 in Science, and we got this beautiful front page. Thank you.